So I'm sure you remember the multinomial logistic regression. We went through it. I guess it was last session and the previous session. So neural networks are gonna generalize that concept. What you have here is a linear model. It's linear in your parameters. And because it is linear, it's gonna be limited in its power. Now we want to go over neural networks as a nonlinear extension of logistic regression. So what did we do for our logistic regression? We had x1, x2, x3, and x4 as our features. We had some parameters. This was for the bias or the intercept, and these are the coefficients in front of your variables. And then this gave us z1, z2, and z3. But the problem with that is that these numbers are from negative infinity to positive infinity. What we need are the probabilities of our classes, because we are not doing regression anymore. We are doing classification. We want to know what is the probability that these features, x1, x2, x3, x4, is going to give us class 1 versus class 2 versus class 3. So we turn them into probabilities. This function is called softmax. It's going to take a function, a number from negative infinity to positive infinity, and it's going to make it into a probability so that p1 plus p2 plus p3 is 1, and then these numbers are positive and less than 1. And then this is going to be your loss function. This we minimized, and it gave us some good results. I guess it was around 68% accurate. Now what we are going to do is generalize that and make that nonlinear. So we're going to make that nonlinear, and we're going to have multiple layers. And I'm going to tell you what each layer means. This last layer from this point to the next one, to our three classes, P1, P2, and P3, is exactly what we have up here. Is exactly what you have here. But now you're changing your features. Rather than using x1, x2, x3, and x4, you're using some hidden units. Now the question is, how do you compute these hidden units? You're going to compute these hidden units based on the previous hidden units in the previous layer. Now the question is, what are these hidden layers? How do you compute them? And why is it a more powerful model? So what I'm going to do, this last layer, we were using betas. I'm just going to rename them and use W's. So that's going to be WO, and WO is going to be W output. Okay, so we need three numbers, Z1, Z2, and Z3. These numbers, then we are going to push them through the softmax, and it's going to give us three probabilities. So we're going to need three numbers, Z1, Z2, Z3, and they're going to be here, Z1, Z2, Z3. Then you have seven numbers here, 1, 2, 3, 4, 5, 6, 7. And I'm going to call them H1, 2, H22, H32, H42 up until H72. And 2 is your layer. So we are now at the last layer. It's layer 2, and that's your index 2. And this WO is a subscript. I'm going to use a superscript. So it's not a big deal. It's just notation. Then these are your betas, beta 1, 0, beta 1, 1. Now you have 7 betas per each z, and it's going to be beta 1, 7. Okay, so these are exactly your betas. But now you have 7 of them rather than 4. And each one, rather than using x1 up until x5 or x4, we are using h12, h72. And these are these 7 variables, h1, h2, h3, h4, h5, h6, h7. And these are all scalars. This is a scalar, this is a scalar, that's another scalar being multiplied by these features, by 7 features. So that's going to give you Z1, Z2, Z3, assuming that you know H2, assuming that you know these values. If you know these values, the weights, we are going to train them. We are going to have a loss function, and then we're going to train them, so we don't worry about those. And if you assume that you know H, you're going to be able to compute Z1, Z2, and Z3. Once you have Z1, Z2, Z3, you can push them and turn them into probabilities, and then you can do your classification. It's similar to what we did before. So we didn't change much. Is everything clear so far? Okay, perfect. So if you know H, if you know H2, you can compute your Z's. And these arrows are just these W's. For instance, W11 is going to be the relationship between the output 1 and the hidden layer, the first entry of the hidden layer 2. So that's going to give you 1, 1. This is going to give you 1, 2. This is going to give you 1, 3, this arrow, 1, 4, 1, 5, 1, 6, 1, 7. And then you are going to have a lot of arrows. These are your W's. These are your H, H1, H2, H3 up until H7. And these are your Z's, Z1, Z2, Z3. Perfect. Now the question is, what is H1? What is H2? Etc. You're going to do the same exercise as we just did. Let's compute H21. H in the second layer, the first entry, the first dimension. Forget about this max function for now. I'm just going to remove it. This is your H1 in the second layer. It is going to be a linear combination. So you are linearly combining H1, H from the previous hidden layer. So now you're doing H11, H12, H13, H14, H15. And then each one is going to have its own parameters. And these parameters are going to correspond to these arrows. So that's the first arrow, second arrow, third arrow, fourth arrow, fifth arrow. That's going to give you H1, 2. You do the same thing for H22. You can compute it if you know the previous layer. Dot, dot, dot. It's the same thing. And then in the end, you're going to have H27. The seventh one is a linear combination of these 5 numbers with its own weights. Now, if we only do the linear part, it's going to be very boring. It's going to turn out to be the same as before. It's going to become a linear function, and it's going to become a simple logistic regression. You are just renaming your betas to be multiplications of these W's. So it's going to become very boring. The nonlinearity is going to come from here. You can either put a tan H, it's a hyperbolic tangent function. It's a nonlinear function. And if you want to see what tan H looks like, it looks like this. This is your tan H function. So it's going to look like a function like this. So if you are near 0, it's going to be linear. Otherwise, it's going to become nonlinear. So that's a nonlinearity. That's how you're going to introduce nonlinearity. Another nonlinearity is maximum of this number and 0. And this is called ReLU activation. This is called ReLU. It's called rectified linear unit. It's exactly what I just wrote. It's a maximum of 0 and your number. And if your number is positive, it's going to be a linear function. Otherwise, it's going to turn out to be 0. Okay, this is just a nonlinear function. And if you use that nonlinearity, then you're introducing nonlinearity in your model. Okay, that's why neural networks are nonlinear. Now, we assumed we know H1. We assume that we know these hidden values at the first layer. But how do we compute these? It's the same story as before. We can compute this based on a linear combination of the previous layer, but the cool thing is that the previous layer we know. That's our input features. For instance, this could be petal length, petal width, sepal length, sepal width, if you are doing iris data. So this part we know, these are our x's, x1, x2, x3, and x4. Okay, let's do that. Now we need to know what is h11. We know what is our x1 up until x4. We can linearly combine them with a bunch of weights and a bias, and then we can push that through a nonlinearity. It could be ReLU nonlinearity. Then what is the fifth entry? It's just a linear combination of your x1 up until x4. You push it through a nonlinearity. And that's it. Now I don't owe you anything. I told you exactly, I gave you whatever that we needed for a neural network. First, you get x1 up until x4. You know x1 up until x4. You initialize your weights randomly. Then it's going to give you h1 up until h5. So I gave you these 4 numbers, 1, 2, 3, 4. You knew these arrows. You initialize them randomly. You just do your multiplication and you compute h1, these entries. Now that you know h1, you use the second formula here. You initialize your weights randomly, these arrows, and then these arrows are going to take you to the second layer. Now you know your H2. Once you know your H2, you're going to linearly combine them, and that's going to give you your Z's. Once you know your Z, you can compute your probabilities. Once you compute your probabilities, you have a loss function. You can write down your loss function, and then you minimize this loss function with respect to these arrows. You initialize them randomly, but now as the training data comes in, you keep updating these parameters. You minimize them and then you find the minimum probability. So is everything clear? Any questions? So probably you guys have heard of Keras for deep learning. It's a package, and you have probably heard it in the context of Python. You can actually use Keras in R as well. It's a package on top of TensorFlow. TensorFlow is for deep learning, and Keras is going to be a wrapper, and it's going to help you write deep learning codes in R. So it's going to be a little bit, it's going to take you some time to install it, and you might run into issues, but the cool thing is that most of these issues you can solve them by Googling. If you run into any errors, you just do a Google search and then it's going to tell you how to install it. But once you install it, the rest of it is loading the library. So I just loaded it. Then you're going to create your model. Your model is going to be a Keras sequential model. Okay. I'm going to be using the diamonds data. For the diamonds data, rather than having 4 inputs, you have 7 inputs. Okay, so I'm gonna tell my first layer is gonna have dimension, the input dimension to be 7. So there are 7 variables. And then my next layer is gonna have 128 variables. So I go from a 7-dimensional vector to a 128-dimensional vector. So this could be huge. In this case, it's 1, 2, 3, 4, 5. But in that case that I just defined, it's going to be 128. So that's 128. This nonlinearity that we used, the maximum, this nonlinearity here, maximum of your value and 0, it's called ReLU, and it's called your activation. That's your nonlinearity. So now you just defined it. What did I just do? I defined the first layer. So the layer that takes you from input to your hidden layer 1. So I just defined that. Then we take the outcome and pipe it into a second layer. You're gonna have 128 dimension. So what just happened? You're going from 128 dimension to another 128 dimensional vector. Okay, and the activation is also ReLU. So this is ReLU for the second layer. Then the last layer is gonna take you from dimension 128 to 5, because in that data set, the diamonds data set, you have 5 output dimensions. So you want to classify between 5 classes. So you go from 128 to 5, and then here your activation is going to be softmax. So not only you do your Z's, but also you apply the softmax, this nonlinearity here, to give you probabilities. And that's going to be your last layer. So we created the first layer. This is one layer, second layer, the last layer. This is the first layer, second layer, and the last layer. Now you create your model. We can actually take a look at the model, and it's going to tell you how many parameters are per each layer. Okay, that's our model. And don't worry about these numbers. This should be layer 1 or layer 0, layer 1, layer 2. And it's going to take you from dimension 7 to dimension 128 to dimension 128 to dimension 5. From 7 input variables, we go to 5 output variables. The next step is to tell the model what optimizer you're going to use. So we're going to use Adam optimizer. Don't worry about Adam. It's just gradient descent. So in your advanced classes, you're going to learn about that, but it's just an optimizer. You are going to say what loss function you're going to use, and our loss function is exactly this formula. Okay, if the underlying class is class 2, you are going to increase the probability of class 2 and then decrease the probability of the other classes for that observation. That's called cross entropy. It has a name. And then you're gonna have a metric, and metric is gonna be accuracy, and we know what accuracy is. Okay, we were just reporting it so far in this course. Okay, now you can take a look at your model, and it's gonna have a dense layer, dense 1, dense 2. This we did before. Now it's the time to do the optimization. To do the optimization, we are doing training. We give it our diamonds data, the training data in our diamonds, except for the first column of the data. Why? Because the first column is our output column, is the cut. The rest of them are going to be our variables. It's going to give us 7 variables to work with. Then we are going to give it the cut, that's our categorical variable that we want to do classification on. Then I had to convert it into a vector. So the way that you convert it into a vector, the thing is this variable is categorical, but our network likes numbers. It likes 1, 2, 3, 4, 5. It doesn't like ideal or very good. If you push it through C function, it's going to turn it into numbers. It's going to give you 1, 2, 3, 4, 5. But then the way that Keras works is that it likes the indices to be from 0. So I'm subtracting 1 from all of the indices. Now our classes are going to be 0, 1, 2, 3, 4. These are 5 classes. And then epoch is the number of iterations, that the optimizer is going to go through. And verbose being 2 is going to print out some nice prints for us. And then the batch size is 50. So it's going to process 50 observations per each iteration. To be honest, I was cheating a little bit. I was not honest a little bit. Epoch is going to be the number of times that you go through your data. So each epoch is one round of going through your data, one round of going through the entire data set. And we know that our diamonds data set, what is its size? We know that you have this many observations in your data set. And then we are processing our data set 50 observations at a time. So you're going to take that number, divide it by 50. This is how many iterations of optimization per epoch. So after this many observations, you saw your entire data set once. And then you're doing it 100 times. So if you multiply that by 100, this is the total number of iterations for your optimizer. Okay? So epoch is the one epoch is going through your entire data set. Okay, I'm gonna run this, and then we are gonna take a look at the optimizer. So the loss is going down and your accuracy is going up. So by this point in time, your algorithm saw your data set 29, 30 times, 31 times, etc. So it's doing its optimization. It's going to do it for 100 iterations, for 100 epochs, and it's doing its gradient descent optimization. The accuracy is increasing, the loss is going down, and then we are now at epoch 80, 81, 82. So the computer is doing its job. It's optimizing the parameters for us. Now done. The final accuracy on the training data is 80%, and the loss is 0.47. Now let's take a look at the predictions of the model, and then look at the confusion matrix. Okay, perfect. So our deep neural network is less confused compared to the other methods that we have seen so far. Let's take a look at its accuracy, and the accuracy is around 80%. It's around 81% actually. So it's pretty good. If you compare it to the previous methods that we covered, this is 57% accurate, and this was the naive Bayes. This model was 65%. This is the linear logistic regression, and this one was k nearest neighbor, 72. Okay, that's a nonlinear model, and it's a powerful model, neural networks. But the problem with neural networks is that they are not interpretable. The other models that we covered so far, they are all interpretable. We can interpret its predictions, especially the multinomial logistic regression is really interpretable. You want to know how important is the first feature for predicting the first outcome, you look at this coefficient. If it's really big, it's very important. If it's small, it's not that important. But doing this analysis on neural networks is not that easy. How important is this feature? There are some methods these days doing it, trying to interpret neural networks, but it's not as clean as what you see for linear regression. So there is always this trade-off between accuracy and interpretability. The more accurate your model is, the less interpretable it's going to be. And then the other one was the training. It took some time, but once it is trained, doing the prediction is really fast. So it's going to take not much time. I'm just predicting the entire data set in a fraction of a second. Okay, once the training is done, this is really fast. Any questions so far? So there is a question from George. Perfect. When training, what are pros and cons of a smaller and larger batch sizes? So I'm gonna share with you this script, and then you can play around with these batch sizes. The cool thing about modern computers and modern hardware is that they can process their tasks in parallel. So they are highly parallelizable. It means that they can handle bigger batches. So now I'm running this on my Mac, but if I run this on my GPUs, it's going to be much faster. Okay, but let's try it. Let's try to train a model with a bigger batch, maybe 1000. So it's still really fast, and then it converges much faster because probably this is a good computer. It can process multiple cases at the same time, and it actually gave us a better result. The accuracy previously was 80%, now it's slightly better, or perhaps not. It's as good. And the other question is, what if I want to change my neural network structure? What if I change the number of units to be 256? You need to compile it, and you can take a look at your network. It's 256. Then you can train it. Okay, done. And then you can take a look at your confusion matrix and your accuracy. Slightly lower. So we gave it more parameters, but it gave us less accurate results. Why? Because it probably is starting to overfit our training data. Okay? The more powerful your model is, the more likely it is to overfit. Let's make some other modifications. Let's add another layer. Now your network is deeper. It's also wider. We can compile it and take a look at your model. Now it has 4 layers, and we can train it. Okay, the training is done. Now we can do the prediction on your test data and see what happened. So it's now 80%. I think we are reaching the limits of our method when it comes to this training data. I guess it's as good as it can get. So does that answer your question, George?
I guess I'm a little confused as to what the batch size really does, because it seems like it's just a different way of going through each epoch.
I think that one I can explain using this. Maybe I need to write a little bit of the math. See, when you are doing your optimization, you can do a summation over n from 1 up until n. This could be your entire data set. So this is exactly what's going to happen. You do a summation over the log of your entire data set. And for um, the diamonds data, I guess it was around 35,500, some number like that. So this is your entire data set. Then you use that to compute your gradients with respect to these grades. And once you know your gradients, you can do gradient descent. What the batch size does is approximate these gradients. If I get the gradients from the entire data set, that's going to be a perfect gradient. There is no approximation. But then summing over your entire data set is slow. Okay, that's why you do the summation up until your batch size. I'm going to call that n batch. And then each time you're going to subsample a random batch of your data, a random mini batch. And this number, we first set it to be 50. And the gradient that you're going to get out of this loss are not going to be as accurate as before. They're going to be noisy. That's why it's called a stochastic gradient descent. So you don't need to understand every single detail. These are more advanced topics. But this is where the effect of batch size is going to come in. One, it is faster to compute this summation. And the other one is that your epoch is going to have more iterations the smaller your batch size is. Then we change that into 100 or 1000. That's your batch size. This you use to compute your gradients. So does that answer your question now? Okay, let's go down here and take a look at our diamond data again. Its dimension was, this could be your batch size. And now each epoch, is gonna take, yeah, I need to compile the model first. So I change the model a little bit. That's our model. That's the training data. Now the gradients that we got here are perfect, but then in the end, our accuracy is not that great because now you're doing less iterations of your optimizer. Probably if I change this into 1000. So any questions in the meantime while this is trained? Now each epoch is one iteration because our batch size is the entire dataset. But previously each epoch was around 300 iterations of optimizer. And the cool thing about neural networks is that it's a big data set algorithm. Now our model is simple and the data set is not that big. If your data set has millions of observations in it, then you can no longer set this to be a million. It's going to take your algorithm forever to compute even a single iteration. Now this is converged. So you can do the confusion matrix, then it's giving you less accurate results slightly. Okay, is everything clear? With batch size, with the way you define your model, with the way that you use the Keras library. So this Keras library, you can use it for images, you can use it for text data. This is a very simple model that I just defined. And those types of concepts you're going to see in your more advanced classes. So how to work with convolutional neural networks, how to work with recurrent neural networks, LSTMs, attention models, etc. This is just the beginning. These are really powerful models. I think there is not much time for me to go to support vector machines. That we are going to do next session. If there are any other questions, I'll be around. And for those of you who want to leave, you can leave.